Dear viewers, I welcome you to the second class number 2 of convection. In particular, we are speaking about forced convection. Okay, in last class I have given you the complete introduction part, and I have also mentioned in this class we will be studying about velocity boundary layer. Fine. So whatever I will be writing here in this sheet, whatever I will be explaining with the help of this first sheet, this sheet is the content which has to be presented in your exam, and I will be writing few of the contents in the second sheet where I don't have a diagram. This is for your understanding, right? So now in velocity boundary layer I have mentioned that this comes under forced convection in the previous class itself. The shaded part over here, this is a flat surface, okay, and the beginning end is called as leading edge. This is the leading edge, and this is trailing edge. So from these words I will come to know that there is a source from where I am getting a air, flow of air. So from this point I have a flow of air. I am blowing a air either with the help of fan or blower. Fine. So now y-axis is the distance normal to this plate. Okay, fine. So now before explaining velocity boundary layer, you should be knowing few of the concepts like Newton's law of viscosity. I know you have come across this, but let's have a revision. What does this Newton's law of viscosity say? What does it say? It says that the shear stress is proportional to the velocity gradient. Okay, this is applicable for a flow of fluid, right? So from this diagram I said there is a flow of air from this end, there is a flow of air on this flat surface. So air is flowing. While this air is flowing here, it should obey law of viscosity, which says the shear stress is proportional to dv by dy. So this part over here, this is called as velocity gradient. Fine. What does this word gradient means? It means that this velocity, this parameter, varies with respect to the length or a distance. So as the distance along y direction increases, there is a change in velocity. Okay, that's what it means. So removing this proportionality sign, I can say it is mu into dv by dy. Fine. So here you need to understand that velocity varies with respect to the distance based on its viscosity. Fine. Law everyone will be knowing. Try to understand its meaning. I repeat, velocity will be varying with respect to the distance from the flat surface based on its viscosity. Fine. So what is this viscosity? Mu. It is called as dynamic viscosity. This is the second parameter. Dynamic viscosity or just a viscosity. Fine. So what was this? Again, by definition you already know, if there are number of layers of fluid, one of the layer will be having an opposing force to resist the motion of the second layer, right? And this second layer will oppose the motion of the third layer likewise. So the frictional force which opposes the flow of one layer to the other, this concept is called as viscosity. This is what you have learned by definition. Now let us apply the same thing for a plate. Say this is a plate. I have a layer of fluid. Likewise, you imagine 2 to 3 layers. So this layer is supposed to move because we have kept a fan, but the flat surface here tries to resist this motion because of a friction. These are the two different bodies which are coming in contact. It tries to resist this flow, and in turn this layer reduces the velocity for this layer, second layer, right? But again, don't forget that we have kept a fan. It will push the air. Even though we have a resistance, it will push the air. Likewise, the velocity will be more at the particular distance, say at the top end, but when it comes to the flat surface, here velocity will be less. Okay, so here it is less. As it goes away from the flat surface, here it will be more because there is no much more resistance over there. Fine. So coming back to this concept, viscosity, this is the meaning of viscosity. And we have something called as kinematic viscosity also. What is that kinematic viscosity? It's the ratio of dynamic viscosity by density. We call that one as mu by rho. Easy to remember, d by d. Okay, so this is kinematic viscosity. Okay, so now again come back to this concept viscosity. Here there is a resistance force, right, which can be called as frictional force, and this is continued from one layer to another layer because of the concept called as viscosity. So I'll be terming the term called as viscous force or force of viscosity. Remember this term because in next parameter we will be defining it. Reynolds number we will be defining in a sense, we will be using it. Reynolds number says is the ratio of inertial force to the viscous force. This is the meaning of, so this is the definition of Reynolds number, which says that it is the ratio of inertial force to the viscous force. Now look, we already know for laminar flow Reynolds number will be less, and for turbulent flow Reynolds number will be more, and in between these two there is something called as transition state, right? So how does this come into picture? In a sense, by the concept of this viscous force and the inertial force. This ratio is called as Reynolds number. So now since air is flowing, it has some velocity by the concept of inertia, so that force should be divided by the viscous force. What happens in laminar flow is this viscous force will be more, fine, so its velocity will be reduced. Okay, and hence since we have a higher denominator, we will get lower Reynolds number. If the viscous force is less, then we will get higher Reynolds number, concept number 1. On the other hand, for the same fluid, if inertial force is less, we will get again lesser Reynolds number. If the inertial force is more, we will get higher Reynolds number. So this is the game completely played by this viscous force, fine, which is more nearer the surface and less at the top. Okay, fine. Now coming back to the actual concept. So this is the plate and this is the velocity distribution. I told you velocity will be less over the flat surface. At this surface it will be less. As the frictional force goes on reducing, viscous force goes on reducing, so the velocity goes on increasing. At some certain distance, say delta, this velocity reaches to the maximum value. Okay, and here the flow is completely free, so this part we'll mention it like free stream velocity. Here it is free stream velocity, which is indicated by u infinity. It is a free stream velocity, and velocity here will be v naught, that is equal to 0. Done. So now velocity is being increased from the flat surface as the distance increases. At some particular distance called as delta, at a particular distance of this fluid, at a particular thickness of this fluid delta, velocity reaches to maximum value, and from here velocity remains same. We have something like uniform velocity. Okay, so now it is called as free stream velocity, and we have this in like a laminar flow for some particular distance along the x. So that distance is called as x critical. Okay, so x critical is that distance up to which we have laminar flow. Okay, here it is a laminar flow. In between these two, I'll get a transition state, transition flow, and here I'll get turbulent flow. If it is turbulent flow, then I should be getting many more eddies. Say whirls will be created, eddies will be created over here. Likewise, that means there is no order of the flow. Okay, so now here the distance up to which we have laminar flow is called as x critical. Okay, and you have to write all the story of viscosity, how does it varies and all. Okay, and here the maximum velocity that it can obtain is free stream velocity. It starts from 0. So I can have a boundary layer over here. This line is called as a boundary layer. I'll mark it in black. So this is a boundary layer which comes in the concept of forced convection. Okay, so now after this we have a transition state. Later again we'll get a turbulent. Now the reasons beyond these things you need to explain it in this manner. After this critical value of thickness, velocity have this kind of variation because of Reynolds number over here. Viscous force is more and here it is less. Fine. So by the time it reaches to some particular distance, inertial force will be more. It carries some inertial force. So viscosity fails to oppose that force, and hence we'll have a transition phase. Okay, I told you it's a game of viscosity and inertial force. And by the time it reaches over here, you can make a note from this point to this point, this distance, it is called as viscosity sublayer, and here this is called as buffer layer. What is this buffering layer? In this sense, look at the change in velocity. Here it is minimum. Fine, it is trying to increase from this point to this point. It has been increased all of a sudden, so it is called as buffering layer, where velocity increases drastically with no time. But here it takes some time. This is because of the effect of viscosity, and hence this layer here is called as viscous sublayer or viscosity sublayer. And above this we have buffer layer. Above this we have a turbulent flow. Okay, you can just imagine a fan which is kept over here on the flat surface and make a air to blow. In the initial stage we'll have a laminar flow, but as soon as the distance increases we'll get a turbulent flow. Now the distance at which we obtain this free stream of velocity starting from the 0 will have a smooth curve, and this curve is called as velocity boundary layer. Velocity boundary layer. Okay, now why does this comes into picture? In the sense, while solving numerical, without our limitations we cannot solve it, right? Without having a limit, we have solved numericals in module 1 and 2. As soon as we write a equation, we'll define the limits, upper limit and lower limit, right? So now here we cannot define it like upper and lower limit, because the effect of this velocity is there throughout the plate, and yes, it is varying. The velocity over here is not same compared to the trailing edge. There is a variation, right? So all this variation will be there within this particular layer. Starting from here, imagine a layer. So within this particular layer we have all kind of disturbances, all kind of variations. So this region over here is something like a controlled space. Okay, and this is the layer which is differentiating the flow from the region where there is no viscous effect, where we have a complete maximum velocity, and the region where velocity is being varied. So these two regions are differentiated with the help of this line, with the help of that layer which is called as velocity boundary layer. Whenever we analyze the numericals, we need to define this velocity boundary layer. So the equation below this region will be something different, and the equations after this will be something different. That's the way we need to analyze. Fine. I hope you have understood this concept of velocity boundary layer, but in order to understand this, you should be knowing all the basics over here in the sheet. Whatever I have written, these basics you should be knowing. You can define this parameter. Okay, you can explain the same viscosity force, how does it vary, fine, in this sheet. Okay, along with that you need to write this diagram. Fine. If you have any queries, in my class 10 of heat exchangers, I have given you a mail ID. You can write it to me. Thank you.